So let's start. Good morning, everybody. My name is Gabriel Santos Pereira, and I'm from Brazil, Universidade Federal de Minas Gerais. My advisor is Professor Carlos, and today I'm going to present Global Optimal State Feedback Control, enforcing safety and cooperation of traffic lights using tropical algebra. I hope you enjoy it. So, let's begin with the motivation. Modern traffic systems require very efficient and safe synchronization, and we need to optimize this in Brazil because we have a large amount of vehicles and people trying to cross the downtown of the center, the downtown of the cities, and well, we think that tropical algebra is an efficiency and simple, low-cost tool to optimize this kind of system. So today I'm going to try to answer two main questions. Well, is it possible to synthesize a global state feedback controller unifying all network constraints? And can we enforce just-in-time behavior, delaying even firings as much as possible while guaranteeing safety? So this image is a spoiler. I think I can try to explain a little bit. We have small systems, like small crossings represented by the edges, controlled by local controllers, and then we have a big controller, the feedback controller, that will try to enforce a just-in-time behavior for all the small systems. This is the outline of my presentation. I will try to model a small traffic signal using time and event graph. Then I will move to tropical algebra. I will explain in a few words what is the tropical algebra. Then I will introduce the control problem and a small example. So let's start with the definition of a timed event graph. Here we have an image. We have an image that is representing a single traffic signal with 3 places, 3 transitions, 6 arcs, well, each place is representing a color state of the signal. So, for example, the signal, when it is green, the token must be in the place with gamma time. So you have the 3 times, the gamma, the alpha, and the beta. So the alpha is for yellow, beta is for red, and gamma is for green. And all the transitions of my time and event graph, they are all controllable. Okay, just to remind, time and event graph are a class of pattern nets. When we move from a simple traffic signal to a pair of them representing a small crossing, we need to avoid collisions. And how can we guarantee that? Imagine that you have 2 signals we are representing by E and F, and we want them to do not allow traffic simultaneously. How can we do that? Well, we add 2 control places that we want to guarantee that the transition to green of one signal only happens after the transition to red of the other signal. And we have another problem. Imagine that you have 2 signals again, E and F, but the F now is in another position. It's in a sequel, and there is a street crossing between these 2 signals. And we want E to only open if F is already open, because if not, there will be trapped vehicles in the middle of this street, blocking another cars to cross. So how can we do that? We add intermediate control places to enforce that E only opens after F is open, and to enforce that F only closes after E is closed. This control, it is what I'm calling the local controllers of my network, and they can be crafted manually because they are very simple. Here I will move from the time and event graph to the conventional algebra equations. So after we can move to the max plus algebra. Okay, as you can see, a signal can be fully described by two main operations, delay and synchronization. So think about this. You have a signal that wants to open, but it can only open if it's already on the red phase, delayed with the beta, and it will be the time that it will turns into green, it will be the maximum between the date that he turns red plus beta and the control that is guaranteeing that the other signals are red or green, because you need to enforce the synchronization with its pair. Okay. Just a few algebraic notations here. I hope you understand, because we don't have enough time to explain all the tropical algebra. But what we have here simply is the maximization will be represented by the signal O plus. The operation in conventional algebra plus is translated to O times in the tropical algebra, and the neutral elements for O plus, epsilon equals to minus infinite, because if you want to maximize minus infinite, if any other element, it will be this element. And if you have O times, the neutral element is E, that is equals to 0, because if you want to sum 0 with any number, it will be still the number. For matrix operations, O times is similar to the product of matrices in the conventional algebra, and maximization, the O plus, will be similar to the sum of matrices. We will utilize residuation theory to find the greatest solution for inequalities, and we will use clean star operator to make an implicit equation explicit. Okay, so regardless of topology, the system's dynamic behavior is generalized into a unified implicit framework, where xk is the state vector containing the dates of the kth firing of all system transitions. A0 and A1 are the matrices where the coefficients correspond to the physical times, alpha, beta, and gamma, and they will map the interconnections between each traffic signal and its predecessors, enforcing delay and synchronization. UK is the control vector responsible for the external regulation, so we can develop a control vector here. And just a remark, n is 3 times the number of traffic signals. So for example, if you have 5 traffic signals, n will be 15. Okay, so here I'm representing the tropical equations for the time invariant graph of the restrictive operation. Just an example. Another example for the cooperative operation, where you have the local controllers attached to the time invariant graph. And finally, we can propose the global just-in-time controller that is the main idea of this presentation. Well, the global just-in-time controller will keep the local controllers and will add the feedback matrix that we are going to calculate. And as I said before, the edges are the small pairs of our network, and they are all being controlled by local controllers, and I want to connect all of them with the feedback controller in order to enforce a just-in-time behavior. So, when we substitute UK in the max plus linear system, we will have an implicit equation, and we can apply clean star operator to solve it. And if we manipulate, we will have the two main matrices A and B. They will just help us to manipulate in order to achieve the feedback matrix that we want. Well, here we have the main result. I'm not going to explain every single step, but we can discuss this after the presentation, of course. So, our primary objective was to synthesize a controller that maximizes the firing dates without violating the original cycle. And our constraint was to maintain our original cycle. So the closed loop, the controlled system evolution must satisfy this equation, and which leads us directly to the agent structure classical problem. And with a lot of clean and a lot of residuation, we can have the main result presented in the slide. There are a lot of steps between 7 and 8, but I'm not going to present it right now. Okay, I hope you understand it. So here I am detailing the system architecture, where we have n pairs of traffic signals. We can have cooperative pairs, restrictive pairs, and all of them are being controlled by feedback matrix. Every single transition of my network knows the other transitions, the state of the other systems. And as you can see, the feedback has 15 per 15 because it is n, wait, it's from the example, you understand it. The size of the feedback is n times n because you have n is, as I said before, n is 3 times the number of traffic signal, and each traffic signal have 3 transitions. So you have the number of transitions and the number of transitions. It's a really number of places, and each place is connecting each transition to the another transitions. A little bit confusing. Here we decided to pick an important crossing from my city, Belo Horizonte. It's an important crossing because it is in the Contorno Avenue. It circles the whole downtown, and you have big shopping malls, schools, and well, you need to enforce a safe and efficient operation because you don't want to stop and wait your whole life to cross the street. And in Brazil, this is a problem because if you have like a fault in a signal, probably all the signals will turn into yellow, and you need to wait for a cop to go there and control the cross manually, and this is a problem. So this crossing, I was there, I collected the times, here the table. The cycle time, lambda, is equal to 120 seconds. The initial firing dates of each transitions are presented here, and I denoted the restrictive and the cooperative pairs. So for example, S1 is restrictive with S4 because S1 and S4 cannot open in the same time, can't be opened at the same time. And also S2 and S3, they are an example of the cooperative pair because S2 can only open if S3 is already open. Okay? And well, imagine that we have 4 local controllers here, each one for each pair, and I'm going to develop a feedback controller that will connect every single signal in order to enforce the just-in-time behavior. This is the F matrix obtained from the software computation. Just an example to show you. For example, we have 5 traffic signals, and so this matrix is 15 per 15, the size. It's very big. And you can note that the main diagonal has the aging value, that is 120 seconds. Because of course, if you note the cycle of a transition to its transition, it must be 120 seconds. Well, and this computation is really, really fast because tropical algebra is low cost for the computer. And to illustrate an advantage of this controller, we will impose an unexpected delay fault on a random transition. So a random transition will be delayed, and we want to see what happened with the other traffic signals. It's just a small example, and we can optimize the system even more, developing if we create other parameters. Here we just want to enforce the just-in-time behavior, and you will see what happens. Okay, so our fault delay occurred in signal 3. We have the 5 graphs. Signal 3 is the one that suffered the fault. And let me explain to you. When the graph is in the 1, you have green, 0.5 is yellow, and 0 is red. The blue line represents the controlled system, and the dashed greens, the dashed waves, they are representing the open loop system. And as you can see, when the traffic signal 3 suffered the tau delay, for the open loop system, signal 2 is still open. And if this happens, look, if signal 3 remains closed and signal 2 opens, we have a problem because there will be crashes. There will be trapped vehicles. And this is a problem for us. And now I'm going to show you the closed loop, only the closed loop. So as you can see, when the signal 3 suffered the delay, every other signal suffered for the same delay. Because think about this. Why do I need to close, for example, the signal 4? Why does it need to close if it is not required to close right now? It is interesting for us to keep all the network stopped at the state because we know that this state is safe and possible. And when the signal 3 suffers the tau fault, all the other signals were compensated. And well, as I said, it's just a small example, and we can develop with another parameters even better feedback controllers to enforce another type of operation. So, concluding, we have developed a global just-in-time control using tropical algebra. And a main topic that I would like to say is it promotes energy savings by minimizing unnecessary waiting times and hand-like holdings during failure scenarios, because we stop all the system. And for further works, we are working on system resilience, because we want to prove that the system is resilient, but we still don't have this formal proof. Okay. These are my acknowledgements. I would like to thank Universidade Federal de Minas Gerais, Conselho Nacional de Desenvolvimento Científico e Tecnológico, Coordenação de Aperfeiçoamento de Pessoal de Nível Superior, especialmente também o Colegiado de Engenharia de Controle e Automação. Patrícia faz parte dele também, do colegiado. Well, thank you very much. These are my contacts. And before I finish, I would just like to thank you everyone for coming to this talk, because I'm just an undergraduate student, and it was a great experience to be here. It was my first time, and thank you very much.